Embodied AI faces a fundamental data bottleneck because physical skills cannot simply be scraped from the internet. To build intelligent robots, models must capture how first-person perception, whole-body motion, object states, sound, and touch evolve together. Existing datasets typically fragment these modalities, leaving the perception-action loop only partially observed. To solve this, researchers introduced the Ambient Capture Engine, or ACE. ACE transforms real home environments into spatially and temporally calibrated recording studios, capturing synchronized multi-sensory streams as humans naturally perform household tasks. To understand why a new capture system is necessary, we must look at the three major limitations of existing datasets. First, they suffer from fragmented modalities. Some offer natural behavior but lack ground truth motion, while others provide accurate poses but omit egocentric views, audio, or touch. Second, they are often recorded in unnatural, sparse laboratory environments that eliminate real-world occlusions and clutter. Finally, most datasets focus on short horizon, single-step actions lasting only seconds, whereas real household activities are goal-directed and unfold over minutes or hours. The Ambient Capture Engine solves these challenges by operating at two complementary spatial scales. The first is a table-scale configuration, which uses densely arranged close-range cameras and high-resolution tactile gloves to resolve fine-grained hand-object manipulation. The second is a room-scale configuration, where sensors span an entire furnished apartment to record whole-body motion, locomotion, and interactions distributed across the scene. Despite their different spatial scopes, both configurations register all data into a single, unified spatiotemporal frame. Achieving precise temporal and spatial synchronization across heterogeneous sensors is a massive technical challenge. ACE achieves this through a robust multimodal pipeline. For temporal alignment, the system uses hardware triggers for exocentric cameras, while egocentric cameras are aligned by visually recording a high-resolution digital clock. Tactile gloves are synchronized with the headset using correlated IMU motion templates. For spatial calibration, an Hierarchical board with retroreflective corner markers bridges the gap between the infrared motion capture system and the RGB cameras, reducing reprojection errors to the millimeter level. Using this pipeline, the authors collected ACE-Data-0, a massive multimodal dataset of daily living activities. It contains over 150 hours of synchronized data, comprising 17 million video frames and 75,000 interaction episodes. 50 participants performed tasks across 200 categories, including cooking, cleaning, and exercising. Crucially, participants were given goal-level instructions rather than rigid scripts. This allowed natural behavioral variations, such as planning, hesitating, and improvising, to be preserved in the data. To evaluate current AI models, the authors established a three-level hierarchical benchmark that mirrors the perceptual capabilities of an embodied agent. The first level targets low-level signals, specifically predicting tactile pressure maps directly from visual observations. The second level focuses on scene components, evaluating how accurately models can reconstruct 3D human body poses from video. The third level evaluates embodied interactions, testing hand motion reconstruction from both egocentric and exocentric perspectives. The benchmark evaluations revealed significant performance gaps in state-of-the-art models. For low-level signals, models struggled to predict precise tactile pressure distributions under hand-object occlusion. For scene components, while models estimated local body poses reasonably well, they suffered from severe drift when recovering global trajectories over long sequences. Finally, for hand motion, egocentric models performed worse than exocentric ones due to extreme camera ego motion and perspective distortion, highlighting the need for multi-view fusion. While ACE-Data-0 represents a major leap forward, it has a few key limitations. First, it currently covers only 2 physical sites, which limits the diversity of room layouts and lighting. Second, ground truth tracking is restricted to pre-scanned rigid objects, meaning the dataset cannot track state changes in fluids, deformable materials, or articulated mechanisms. Finally, the physical capture equipment, including the motion capture suits and tactile gloves, is visible in the videos, which could introduce dataset-specific visual biases. In conclusion, ACE-Data-0 provides an unprecedented, unified foundation for the future of embodied AI. By delivering synchronized human demonstrations with aligned perceptual, kinematic, and contact supervision, it opens up new avenues for imitation learning, world models, and vision-language action systems. This work moves us closer to a future where robots can seamlessly perceive, plan, and physically interact within complex, real-world human environments.